Hello everyone, this is a presentation for IROS 2020. The title is Multitask Control for Quadruped Robot with Changeable leg configuration. I am the first author, Linqi Ye, from Tsinghua University. First of all, the contributions of this paper are summarized as follows. Firstly, we designed a modular quadruped robot named THU Quad2 using integrated joint modulus. Secondly, we have paid special attention to ensure a wide range of motion for all the joints, which allows the robot to have multiple configurations, including mammal-type configurations with bidirectional knees and sprawling-type configuration. Thirdly, we demonstrate that even some challenging locomotion tasks such as docile stealth and stones can be achieved in a rather simple way without using complicated control algorithms, which suggests us to rethink about the leg configurations in designing quadruped robots. Our motivation comes from other quadruped robots. We have examined many other quadruped robots and found that two configurations are very popular. One is the forward-backward configuration, which means the hind leg bends forward while the front leg bends backward. The representatives are HYQ, big dog, little dog, star ETH, and any more. Another type is the backward-backward configuration, where all the legs are bending backward. Typical examples are Sport Mini, Vision 60, 绝影, Like I Go, and Armored Cheetah. For most of these quadruped robots, their leg bending direction cannot be changed due to joint angle limit. But there are two exceptions. One is the animal quadruped robot. It uses a linking mechanism with offset, which allows a full rotation for all the joints, and it can exhibit various configurations as shown in this figure. Another one is the Armored Cheetah. It uses a belt drill for the knee joint, which allows it to change between different configurations. Another motivation comes from the Titan robot, which is a sprawling-type quadruped robot. As can be seen from this figure, the legs of a sprawling-type robot are very similar to the insect's leg, and the center of gravity is much lower compared to a mammal-type quadruped robot. This gives a particular advantage for this type of robot when working on uneven terrains, since they are less likely to fall due to a lower center of gravity. Motivated by the aforementioned quadruped robots, we are aiming to building a quadruped robot that have multiple configurations, including both mammal type and sprawling type, so that it can take full advantages of different configurations. To this end, we built a quadruped robot, THU Quad2. Compared to its previous version, THU Quad2 has adopted a new linking mechanism, as shown in this figure. The new linking mechanism has an offset between the leg links. It allows the joint to gain a wide range of motion, which is approximately 330 degrees for both the HFE and KFE joints. This enables our robot to exhibit multiple configurations. Besides, we also add wheels to THU Quad2 so it can move rapidly on level ground. Formally, we define 5 configurations for our prototype quadruped robot. 4 of them are mammal type configurations, including backward standing, forward standing, outward standing, and inward standing. The rest is the sprawling type configuration. While the robot can support its body either with legs or wheels, but the knees are always above the body to keep a low center of gravity. In some particular scenarios as shown in this figure, one of the configurations can be much better than the others. For example, if the leg bends in this way, it is less possible to collide with the styles. But if the leg bends in this way, the collision risk is very high. Therefore, we use a simple rule to determine the leg bending direction. That is, always bending legs to the downstairs or downhill direction. In this way, we can reduce the collision risk of the legs with the local environments as far as possible. To control our robot, we propose a multitask control framework. In this framework, configuration selection and gate planning are two key elements which cooperate with each other to conquer multiple tasks. For a given task, the robot first selects the most appropriate leg configuration and then adopts the corresponding gates. During a task or when transferred to another task, the best configuration may change, and the robot needs to make decision to switch to another configuration. Therefore, the configuration selection modular gives us more flexibility when facing different tasks. Here we specify how to switch between different configurations. As can be seen here, the 4 kinds of mammal type configurations can convert to each other directly. We can calculate the joint angles according to a simple equation and then use joint position control to convert into the desired mammal type configuration. As for the sprawling type configuration, it can be obtained from the outward standing configuration. When doing this, we use the inverse kinematics control mode and let the foot to move along an incorrect line. And the robot can also do the inverse transition. Then we design 3 categories of gates for the robot. 2 of them are mammal-like gates, which can be applied to all the mammal type configurations. These gates including a walking gate for level ground and gap, and a climbing gate, which is used for stairs, slopes, and docile. The remaining one is the sprawling type gate, which we call as clawing gates, and it is used for uneven terrain. All of the gates are designed with a carefully selected motion sequence under static stability. To cover environments with different size, all the gates are designed as standard parametric gates, while the gate parameters can be adjusted to adapt to different environments. For example, both the walking gates and the clawing gates only have one gate parameter, the walking distance d, while the climbing gate has 4 gate parameters. Now let's watch a video for the simulation and experimental results. The first is a docile and steep stealth task. We can see the robot changing its leg configuration twice when crossing the docile. After that, it transfers to the backward standing configuration to climb the steep stealth. In this way, the robot can prevent its legs from colliding with the docile or stealth. The second task is a stealth and slope task. We show a comparison of the simulation and experimental results. The simulation is performed in the VRIP software, and the experiments are controlled with offline data from the simulation. We can see they coincide very well. The last task is sand and stones. The robot first walks through an area with sand. Then it transfers into the sprawling tab and uses the clawing gate to traverse the stones. In this way, it can move very stable and efficient. So, to summarize, we have built a quadruped robot, THU Quadruped. It can change the leg bending direction in marble tab configuration, which makes it to better adapt to stealth and slopes. It can also use sprawling tab configuration, which guarantees robust locomotion on uneven terrains. In summary, our strategy by using multi-configuration and simple control is proved to be very effective to conquer a variety of challenging terrains. We are also designing a new quadruped robot, THU Quad 3. It is equipped with visual sensors and a reconfigurable arm. Our future work will focus on autonomous detection of the terrains and manipulation using the reconfigurable arm. That's all of the presentation. Thank you.